Welcome everyone to the webinar, Assessing the Benefits and Risk of Quantum Computers. My name is Jason Lee. I'm one of the ATARC's Global Quantum Working Group government co-chairs. We are very excited to welcome Dr. Travis Schulten to speak with us today. Dr. Schulten works as the technical lead for the public sector at IBM Quantum. He focuses on large and strategic activities with government entities to identify opportunities for leveraging quantum computers and advances in quantum computational science to drive technical and economic impact. In this talk, he will present on assessing the benefits and risks of quantum computers. If you have any questions, please feel free to use the Q&A feature. We will save Q&A for the end. Thank you. Dr. Schulten, please take it away.
Thank you very much, Jason. Glad to be here today. The purpose of this talk is to do a review of a paper that I and some co-authors published on the archive earlier this year. The title in many ways is self-evident. We seek to understand how we can balance the benefits and risks of quantum computers off of one another and try and gain some sense of the timeframes over which those benefits and risks might manifest themselves. We adopted a very large survey of the literature. We examined many different papers, many different perspectives on these matters to try and really gain some understanding of these benefits and these risks. In many ways, our conclusion is in many ways somewhat self-evident, depending upon which side of the spectrum that you find yourself on. Based upon our survey, we conclude that there's a credible expectation that quantum computers will be capable of performing computations which are economically impactful before they will be capable of performing ones which are cryptographically relevant. To unpack that a little bit, it is important to understand that the cybersecurity risk posed by quantum computers manifests itself now. We're aware of the harvest now, decrypt later attack, for example, where adversaries are storing our data and simply waiting for a large enough or capable of quantum computer to decrypt it. So in that sense, a cybersecurity risk is real. But in terms of, what can quantum computers actually compute? What are the kinds of problems that they are capable of solving at various levels of technological maturity? It is our conclusion that over the coming years, we will first see capabilities that perform economically impactful quantum computation, or perhaps also scientifically relevant quantum computation, and that realizing the kind of large-scale cryptographically relevant quantum computers will happen after that. We make no guarantees about the various timescales over which these two activities might occur or the difference in time between them. We just simply observe that in our opinion, there is an ordering. Now you might say, okay, well, why? Why do you conclude this? And there are a variety of factors that the paper outlines, and I'm going to discuss some of them here today. They relate to the development of new kinds of quantum algorithms. Initially, our paper focused on things like variational algorithms. Most recently, there have been other ideas introduced in the literature about clever ways of using quantum computing alongside classical HPC and kind of redefining what the notion of a quantum algorithm is. Over the past several years, there's been a lot of advances in the theory of error mitigation, which is ways of handling the impact of noise in quantum computers today and essentially virtualizing it in a manner that makes a noisy quantum computer emulate a less noisy one. There are new problem decomposition approaches that go by the name of circuit knitting. And a very important factor is the simple fact that the commercial sector has begun exploring in earnest the capabilities of quantum computers, doing proofs of concepts, pilot projects, education, upskilling, learning, etc. These activities all increase the probability of finding some commercially relevant or economically impactful use case. And then the final factor is the activities that have been underway at NIST over the past 8 years in developing post-quantum cryptographic standards. These are the new standards recently released this year, which give us a new kind of cryptographic primitives that we can use to secure our data. So you can find the paper on the archive at the link on the left. And the purpose of this talk is we're just going to walk through some of those factors, explain them in a little bit in more detail, and then as Jason said, we will do Q&A at the end. Now you might wonder, why does this sort of analysis even matter? And a way that I like to take a look at it is through this paper a figure from the paper. In the top, what we're plotting are these resource estimates. So these are complexities of the quantum circuits necessary to solve various kinds of problems. These are rigorous analyses of that complexity. And we've color-coded the ones in the top on the basis of whether or not the problem being solved is cryptographically relevant or not. And you can see that these two clouds of the orange and gray hatches, they overlap on top of one another. There's not a very clear separation between them. And if we envision that the future of quantum computing is, increasing capabilities, then what we imagine is that there's some region that starts in the lower left side of that figure in terms of the complexity of the circuits that quantum computers can run, and that will grow up and to the right as the years go by. The problem here is that because of this overlap, it's not so clear whether or not in pursuing industrially useful or industrially useful or commercially impactful quantum computation, that we might not also accidentally perform cryptographically relevant ones. And so that was the fact that we were trying to get a handle on, is there's this murkiness, this ambiguity of which of these two factors could be realized if we just look at the resource estimates. But the simple fact of the matter is that there have been many different advances in how we can use quantum computers in meaningful ways. The first advance is new quantum algorithms. In the paper, we focused on variational algorithms, as previously stated. Over the past year, there have been these new advances on this notion of quantum-centric supercomputing, which is how we use classical HPC alongside quantum computers in order to do interesting computations that are enabled by the fact that classical computers are really good at performing certain computational tasks, and that you shouldn't be performing those computations using a quantum computer. As an example of this is a recent paper from the IBM Quantum team in collaboration with RIKEN, which is a Japanese scientific research center, using Fugaku, which at the time of the writing of this paper, I believe was one of the top 5 most powerful supercomputers in the world. And the idea was to do interesting kinds of quantum chemistry calculations beyond the capabilities of what brute force classical computation or classical simulation would be able to accomplish. I'm not going to go into the very particular details of the specific example shown on the right-hand side of the slide. The important thing to realize is that in order to get the results in the plots that you are looking at, you had to use an advanced quantum computer, in this case, a quantum system built on top of our Heron architecture, and also actually use a supercomputer. That is, the workflow involved quantum computing resources and classical HPE resources, and utilizing both of those to the maximal extent. And the algorithm that was developed is this notion of sample-based quantum diagonalization. And the idea is that you can use a quantum computer to sample from a wave function. And then you can classically post-process those samples in a problem-dependent way, in this case, the problem being a particular kind of quantum chemistry calculation, using classical HPC. And classical HPC is really good at doing things like diagonalizing matrices and calculating eigenvalues. And so we really shouldn't be using quantum computers to do that. And so this SQD algorithm allows us to take advantage of the best of both worlds in that sense. Now, it was a very complex algorithm because of this dynamic interplay between quantum and classical compute resources, and the partitioning the problem and understanding which parts of the problem have to be solved in what ways on which pieces, which makes it a really interesting research challenge. But it does demonstrate that there are new ways of using quantum computers, new kinds of quantum algorithms that could unlock useful quantum computations. The second factor is this notion of error mitigation. This is a way of limiting the impact of the noise. Now, error mitigation sort of achieved its heyday as a way in last year with the publication from the IBM Quantum team on the cover of Nature. This paper, Evidence for the Utility of Quantum Computing Before Fault Tolerance. And the idea of this paper was to emphasize that using these error mitigation techniques, we could use a noisy quantum computer to produce accurate expectation values or estimates or averages, on circuits that act over 127 qubits and, order 3,000 gates. And that the scale and complexity of those circuits is well outside what brute force classical simulation is capable of doing. And the significance of this result and the results which followed it is that we're entering an interesting world where using error mitigation, we can get hardware results that are essentially kind of acting as like the arbiter of the validity of whatever classical simulation that is being performed to emulate those experiments or understand their behavior. So in that sense, we could start to see quantum computers as becoming a scientific tool for discovery. Like the actual experiment, the name of the game, as it were, is to run some very complex circuit on a quantum computer and then try and understand the results, by building classical models. And so the point of this figure here is to emphasize that one of these colored objects is the results from the quantum computer, and the other colored objects are the results of various classical models that emulate or otherwise simulate the behavior of the quantum computer or the circuits that we're running on it. And you can see that all of these, in some loose way, agree with one another, but there are some differences. And so how do we understand which one is the most accurate, which one is most descriptive of reality? Well, there could be a plausible claim to be made that the one that comes from the quantum computer, because it is actually doing the quantum computation, is the one that most accurately describes reality. The interesting thing about all of these error mitigation techniques as well is that several of them come with provable convergence guarantees. And this means that we can rigorously assess the quality of the results that we're getting back from the quantum hardware. And that in that sense, we can be, very sure of the kinds of comparisons that we're trying to make. Now, since this paper, and the launch of utility scale systems through the IBM Quantum Platform, we have seen our other members of our own team, and we've also seen people externally taking advantage of these systems and using error mitigation and clever algorithmic techniques to do interesting kinds of scientific problems, at this utility scale or sort of order beyond brute force classical simulation, in areas such as simulating molecules, doing quantum optimization problems, doing quantum machine learning, developing new specific methods or techniques to extract the most accuracy out of the systems that you're working on. And so all of these capabilities say, okay, we're moving quantum computing in a direction where brute force classical computation can't really keep up. And even if we develop new approximate methods, well, the results from the quantum computer are probably the ones that we should take as the underlying ground truth, and that we should be comparing those classical results to those results, not vice versa. And so it puts us in a very interesting regime as far as scientific discovery and problem solving is concerned. The other major factor here is the development of use cases in the commercial sector. I joined IBM about 6 years ago, and the first team that I was on there was charged with working with the customers and clients of the IBM Quantum Network. And one of the very interesting things to then observe over the past 6 years is the maturation in the sophistication of commercial industrial end users. In many ways, we have gone from educating people about like, well, what is a qubit and why should I care about quantum computing, to, okay, well, how do we do some interesting kind of proof of concept? How do we identify the limits to scaling that proof of concept? How do we start to think about what it means to integrate these concepts into our industrial scale workflows, so on and so forth. So it's been a really, really exciting time over the past 6 years in that regard. Now, because quantum computing is a computational capability versus a solution in search of a problem per se, it means that there's a wide aperture of different industrial verticals or specific use cases that it could intersect. And shown on the right are, some kind of different industrial verticals and some common use cases that people have tended to find, within them. And this is by no means saying that these are the only industrial verticals, the only use cases, et cetera. It's just simply observing that within these verticals, these are the kinds of problems that different research teams have tended to gravitate towards. Some of them might be more amenable from a domain expertise perspective. Some of them might be more interesting from a business perspective. Some of them might have the most kind of anticipated potential for the usefulness of a quantum computer, and so on and so forth. And again, as I said at the top of the talk, the important aspect here is that in the absence of this exploration, well, it would be very, how do you get to economically impactful quantum computing without a commercial end user ecosystem that's actually using this technology? So that's really the significance here. I think the significance is also validated, and the impact has been validated by this survey from the folks at BCG, which is tracking, kind of proofs of concept in industry by year. It's tracking customer spend, enterprise use case activity, and you can see that this is continuing to grow. And that's a very exciting thing. It's also exciting that the focus is not just within any one particular industrial vertical, right? It's not like one industrial vertical is sort of grabbing onto all of the use case exploration and doing that on their own. This is kind of very broad-based diffusion, as it were, of understanding of quantum computing and its computational capabilities, into the commercial sector. And so the significance thereof, again, is that as the capabilities of quantum computers are maturing, then we have this commercial end user ecosystem, which is also becoming increasingly sophisticated in how it both uses quantum computers and also figures out how to integrate them into their commercial workflows. Then another way of looking at this, which is from the folks at the Quantum Computing Report, in the report linked to in the bottom of the slide, is that if you look at kind of, well, what are the different sort of paradigms that people have been doing in their use cases? You find that in the left-hand figure that the overwhelming paradigm has been, well, like, we actually want to try this. Like, we actually want to figure out how to run this on hardware. We understand that we may need to take some very, very highly complex problem, and we need to simplify it and simplify it and simplify it and simplify it and turn it into the kind of problem that could be run on current or near future quantum hardware. But at least that's the direction that the commercial ecosystem is going. We could juxtapose this against a timeline in which the commercial ecosystem is only doing like the rigorous kinds of resource estimates that I showed in the first figure of the talk, in which case then the translation of those resource estimates and the applications that they unlock into real world use, well, would be a little bit more difficult. And then again, the figure on the right is to again emphasize that that many different industries, are maturing, in their understanding of quantum computing. And so they're moving towards performing, larger scale demonstrations, more sophisticated kinds of problems. We went from boiling the problem all the way down to the simplest possible thing that we could conceivably fit on a quantum computer to starting to add back some of that real world complexity, which is also really important because at the end of the day, you really want to solve the real world problem, in its kind of full gory real world complexity. So these factors that we've just discussed here, new kinds of quantum algorithms, error mitigation, and the commercial exploration of quantum computers, one could conceivably contend that they bring forward in time closer to the present, realizing economically impactful quantum computation. Now, for a couple of these, namely the new algorithms and error mitigation, you might say, well, those are actually just computational techniques. Couldn't they also be applied to Shor's algorithm or some other kind of new quantum factoring algorithm? Like, don't they also bring closer to the present the realization of cryptographically relevant quantum computing? That's a great question. We contend the answer is no. And this is because, based upon our analysis of state-of-the-art algorithms for quantum cryptanalysis, that realizing the kinds of cryptographically relevant quantum computation will require large-scale error correction. So a couple of different ways of looking at this. The first is the figure on the left, where what we're plotting is kind of a number of error opportunities, which is roughly a sort of a measure of the complexity of the quantum circuits involved, against the number of bits of security in terms of an RSA key provided by keys of a given strength. And as you might expect, as we increase the security of the keys, then attacking those keys requires more and more and more complex quantum circuits. And one could argue that the complexity of the quantum circuits here, realizing them without some kind of quantum error correction, and ideally, large scale, highly redundant, highly robust quantum error correction, just seems extremely unlikely. It just seems extremely unlikely that in the absence of error correction, you could run these circuits and get reasonable results. Now, the other way of looking at this is to say, okay, well, let's just see how many times people have tried to do things like factor the number 15 or the number 21 or 35 using quantum computers and real quantum hardware. And that's the table on the right. And what you find is that there's actually been very little progress in terms of state-of-the-art, non-trivial implementations of Shor's algorithm in terms of using real hardware. Now, of course, one might argue, well, but the hardware hasn't been there, Travis, so maybe you just have to wait and see. That's an interesting point. The other point to raise here is that even this year, there have been some new advances, both in terms of using Shor's algorithm and also developing new variants thereof. And one of the things to keep in mind is that when people talk about these keys, you should ask, well, how many bits of security does that key actually provide? Because that's the factor that's really going to matter. It doesn't matter how scary looking the number is in terms of digits on the screen. If it doesn't provide that many bits of security, well, you wouldn't have been using that as a key in the first place. Okay? And of course, in general, the sooner everybody migrates to quantum safe cryptography, the sooner this cybersecurity risk can be remediated, which leads to the last factor, which I guess is on the next slide. I'm sorry. The other aspect that I wanted to talk about here was, yes, there has been an improvement in Shor's factoring algorithm. So that's this set of images on the right-hand side of the screen. And also this guy, Regev, he came up with a new interesting way of doing factoring. It's inspired by Shor's algorithm. And it has some improvements in terms of its asymptotic performance. It requires, some fewer number of gates, but it does require more qubits. And if you go read the abstract for Regev's original paper, he says, quote, "It is currently not clear if the algorithm can lead to improved physical implementations in practice," end quote. And so I raise this primarily because, there are those of you who have been following the cybersecurity literature and quantum computing. And, Regev's algorithm, it's sort of like, it did a spike on Google Trends or something like that. And I think it's important to realize that, yes, those improvements could continue to occur, and that's a very interesting thing for the research community to be doing. But it doesn't seem like just looking at, what we know about this algorithm, that it somehow changes the game, per se, in terms of the realizing cryptographically relevant quantum computing. Okay, so I just wanted to bookmark that for you. And then the final factor here, which actually gets this whole section in the paper, is these NIST standards. So at the time the paper was written and put on the archive in January of this year, NIST had not quite yet released those standards, and now they have here in August of this year. So we now have 3 new FIPS, Federal Information Processing Standards. They're shown here on the right. Major shout out to NIST for this activity. Their first sort of efforts began circa 2016, and they've done a tremendous job of marshaling the community, the cybersecurity community, the security community, the quantum computing community, to really understand, okay, what are the new kinds of computational primitives that we need to put in place? and maybe just for those of you who aren't necessarily most familiar, the idea with these new standards is that these represent new classical methods for encoding or encrypting and decrypting data, where the underlying math in those methods has been sort of argued to be difficult for quantum computers to be able to tackle. That's unlike, for example, currently used encryption systems, particularly RSA, variants thereof, where we know vis-a-vis Shor's algorithm that there's an effective and efficient way for quantum computers to perform an attack. So I'm going to leave you with this quote from Dustin Moody, who was one of the co-authors on the paper. We encourage system administrators to start integrating them into their systems immediately because full integration will take time. I will also point out that the NSA has released, some guidance. There's other guidance from NIST has a cybersecurity center of excellence, I believe, and on net, the U.S. government itself is in its own ways and in timescales that it works over, working on adopting quantum safe cryptography. And so now when we look at the cybersecurity side of the question, we conclude that, okay, things like new kinds of quantum algorithms don't really change the game. You can't use error mitigation. You need error correction. And there's no real commercial, use case development there. And so what this tells us, or at least from our study of this, is that actually, no, all of these advances move forward realizing economically impactful quantum computing, but they don't move forward realizing cryptographically relevant quantum computing. Hence, the conclusion is the economically impactful quantum computing will occur before the cryptographically relevant quantum computing. So with that, I'm going to stop the talk. Happy to take any questions in the Q&A.
Thank you, Dr. Schulten. We appreciate that. I don't currently have any questions in the Q&A module.
Okay.
Does anyone have any questions they want to post in the module or?
Thank you, anonymous attendee.
No, these slides are not currently going to be available for distribution at this time.
Oh, John, you will be able to view this on YouTube. Can I type a yes? I can actually post a link to the paper. Great. Looking at getting a link here. Let's see if I do this. All right, I'm typing it now. There you go. Yeah, if you just Google assessing the benefits and risks of quantum computers, you'll find it on the archive. The archive ID is 2401.16317.
Yep, and even though we're not sharing the slides, as Dr. Schultz said, the presentation that we hear is recorded. It will be available, just not the slides themselves.
I don't know, anonymous attendee. Am I related to Dr. Olaf Scholten, nuclear physicist? I don't think so. I mean, Scholten is a Dutch surname, so there's a lot of us over in that part of Europe. To achieve faster than the lead we have had to achieve commercial uses. That's an interesting question. It's given the evolution of QC, could one expect cryptographically relevant QC to be achieved faster than the lead we have had to commercial uses? I don't know. That's an interesting point. I mean, we've had a long time of thinking about quantum computing for cryptanalysis, not so much first thinking about commercial use cases. Anonymous attendee, how does a practitioner address privacy concerns with QC algorithms, or is this even an issue? Yeah, this is a really interesting point, because right now the dominant programming model is that you're sort of directly telling the platform or provider what sort of circuit that you want to run. And there has been some research which has tried to understand some of the security implications of that. One could reasonably expect that as time goes by, providers are going to provide different kinds of abstractions or entry points into their services, which lessen that concern. What do I think? That's a great question. What do you think of Harvest Now, Decrypt Later in light of your paper? It still seems like a very scary thing. I will say I have a PhD in quantum computing, but it was not on the cybersecurity side of things. So I learned a lot about cybersecurity by working with the tremendous folks, Michele Mosca of Evolution Q and Dustin Moody of NIST and Carl Williams, formerly NIST, and all the co-authors. It's a very real and tangible thing that needs to be taken seriously. I would leave it at that. Yeah, like take it seriously, do what you need to be doing, practice, good cybersecurity hygiene, etc. Absolutely. I have a few more minutes. I'm happy to wait. If you Google, so anonymous attendee asks, who is the NIST agency contact for questions concerning the QC FIPS? I'm not going to say my co-author because I'm not exactly sure if that's the case, but NIST has a whole website. If you Google NIST PQC, like the whole website, a whole team, everything like that, you can learn a lot. Anonymous attendee, how is regevs different from Shor's? So Shor's algorithm uses one very large monolithic circuit that you have to run some number of times to get with high probability the answer to the factoring question. With regevs, in terms of the circuits, it uses circuits which are asymptotically slightly less complex, but you have to use a larger number of them. Brian asks, when implementing QC encryption algorithms in favor of existing classical algorithms, is there inherent risk that a classical computer has any capacity to affect confidentiality of QC encrypted data? I think it's important to clarify that what was being discussed here was classical algorithms that are used to encrypt and decrypt classical data. So it's not like there's no quantum computer or quantum computation in the loop on that at all.
Yes, most of the PQC things going on right now, research and things is around protecting classical computers from quantum computers.
Yeah. I will say in these sorts of situations, I always ask the obligatory, what is the one question that you will have wished that you had asked me when we end our time together today? Thank you, whoever did that smiley face emoji.
They'll think of it as soon as we hang up.
I found that too. It's so funny. You're paying attention. You're thinking like, I'm going to ask the really good question. I know what it is. I know what it is. And then you're like, I have no idea what it is.
Yeah, just
Thank you, Itzel. Jason, I think that question's for you.
Yeah, Amy probably can answer that. The email will go out after the meeting, I believe, to all the participants with the and Amy's typing an answer.
Look at that. Great. Anonymous attendee, your question, any info on QC for law enforcement, is a little vague. And so I'm not quite exactly sure what angle you were looking at there. Law enforcement application use cases. This is a really interesting thing, and I might just use 30 seconds to say that I should hope that one day there's a section in my paper which talks about how the U.S. government has adopted quantum computing, and to date that really hasn't happened. As you might expect, the agencies such as the Department of Energy and the National Science Foundation have been really interested in investing in this technology. Some other agencies like actually NASA as well has been doing a lot of work there. Some work with the Department of Homeland Security. I think what would be really good to see is a little bit more of a concerted effort at the agency level to interface with industry and sort of get that dialogue going, because right now it's a little bit difficult.
All right, that's all the time we have for today. We appreciate everyone's attendance. Thank you, Dr. Schultz.
Thank you, Jason.
We appreciate it. And that's the end of the webinar.